In this video, let's configure Ospf for this topology that we see on screen, and you'll see from the diagram that we want to break this up into a couple of different areas, not because we need two areas. We don't have that many routers. It's not going to be overly taxing on our routers to run the Dijkstra algorithm for the entire topology, but I want to show you how we set up a multi-area Ospf network. Let's begin on router R1. We're going to go into global configuration mode, and then we're going to start up the Ospf routing process. To do that, we say router Ospf, and we give a process ID. This is not an autonomous system like we had with EIGRP. This does not have to match on a neighboring router. It's just a locally significant process ID, and I'll use 1. Now in router configuration mode, I'm going to give a series of network statements. And the network statement is really misunderstood a lot. When I say network and I give a network address and a wildcard mask and an area assignment, a lot of people think that I'm saying I want Ospf to advertise this network. Actually, what we're saying is I want any interface that's in the upstate that has an IP address that is included in the address space specified by the network statement. I want that interface to participate in the Ospf routing process. So I want you to look at the network statement as a command that is saying I want one or more interfaces to participate in Ospf. I do not want you to view the network statement as us saying advertise this network. Let's give the first network statement to make interface fast Ethernet 0/0 participate in this Ospf routing process. Let's say network, and I'm going to give the network address, it's 192.168.1.0, and instead of giving a subnet mask, I'm going to give a wildcard mask. Remember how you calculate a wildcard mask from a subnet mask? For each octet in the subnet mask, you subtract that value from 255. So if I've got a subnet mask, as I do in this case, of 255.255.255.0, in the first octet, it's going to be 255 minus 255, so it's a 0. Same thing for the second octet, same thing for the third octet. Now in the fourth octet, in my subnet mask, I have a 0. So what is 255 minus 0? It's 255. That's my wildcard mask. Now I want to give an area assignment. Any interface that's up and has an IP address within this address space, I want that interface to participate in area 1 in my case. And this is going to include the IP address assigned to fast Ethernet 0/0, so I've now told that interface to participate in Ospf. What about the loopback interface? Let's include that as well. Let's say network 1.1.1.1, and if you notice, the IP address for the loopback 0 interface has a 32-bit subnet mask, meaning that this is a subnet of only one IP address. This is a host IP address. And since our subnet mask is 255.255.255.255, our wildcard mask is going to be all zeros. 0.0.0.0. I want this to participate in area 1 as well. And we've also got fast Ethernet 0/1 connecting down to router R2. Let's make that interface participate in Ospf process ID 1 by saying network 10.0.0.0. It's a 24-bit subnet mask, so our wildcard mask, just as we discussed earlier, is going to be 0.0.0.255, and I want this interface to participate in area 1. We've now completed our Ospf configuration on router R1. Let's move to router R2. Router R2, you might notice, has interfaces in both area 0 and area 1. Do you remember what we call a router like that? It's an ABR, an area border router. An area border router has one or more interfaces in the backbone area, area 0, and it has one or more interfaces in a non-backbone area. And on router R2, we'll go into router configuration mode for Ospf. I could use a different process ID if I wanted to. I could use a 2 or a 200. Just for consistency, I'm going to say 1, but it doesn't have to match up with the process ID that I used on R1. Let's give a network statement that will make my loopback 0 interface on R2 participate in this Ospf routing process. Let's say network 2.2.2.2. We've got a 32-bit subnet mask. That means our wildcard mask is going to be all zeros. And we want the loopback to participate in area 1. However, if you notice the serial 1/0 interface on router R2, it connects out to a frame relay service provider. And even though it's a single interface, it's subdivided into a couple of sub-interfaces, serial 1/0.1 and serial 1/0.2. And these are configured as point-to-point subinterfaces, so they're going to have IP addresses in different subnets. We've got two different subnets that we want to participate in this OSPF routing process. Let's say network 192.168.0.0, and for this subnet, we've got a subnet mask of 255.255.255.252. That's a 30-bit subnet mask. So if we subtract the value in each of those octets from a 255, that's going to give us a wildcard mask of 0.0.0.3. And we want an interface belonging to this address space to participate not in area 1, but in the backbone area, area 0. Let's give another network statement for our other subinterface. Let's say network 192.168.0.4, same wildcard mask 0.0.0.3, and we want an interface in that address space to participate in area 0. You might notice that there's one other interface we haven't done yet. It's interface fast Ethernet 0/0 connecting up to router R1. What I want to do with that interface is show you an alternate way of telling an interface to participate in an OSPF routing process. After all, the purpose in life for a network statement is to have interfaces participating in the routing process, so why not just tell the interface directly? We can do that. Let's go into interface fast Ethernet 0/0, and we're going to say IP OSPF, and we give the process ID, and we specify the area assignment. We say area 1. We're saying that we want this interface to participate in OSPF process ID 1, and we want it to belong to area 1. And we should see an adjacency come up between routers R2 and R1. You see that we have a neighbor at an IP address of 1.1.1.1. That's the router ID, that's the loopback interface of router R1, and our state is full, meaning that we have fully formed an adjacency with router R1. We're now done on router R2. Let's exit out of this and go to router R3. On router R3, let's go into router configuration mode for OSPF. And again, just for consistency, I don't have to, but I'm going to use a process ID of a 1, and I want to show you another shortcut. Yes, I could give multiple network statements to make the loopback interface and my two sub-interfaces and the fast Ethernet interface participate in this OSPF routing process. However, if you notice, on router R3, all of my interfaces need to belong to area 0. If you've got a situation like this where all of the interfaces on a router need to belong to the same OSPF area, you can give a very general, a very generic network statement that will encompass all IP addresses. That means any of your interfaces that are currently up that have an IP address, they're going to be included in this very generic network statement. Here's the network statement. We say network 0.0.0.0, and then for the wildcard mask, we're going to give all 255s, meaning that we have a subnet mask of all zeros. This is going to include all IP version 4 addresses. With a subnet mask of all zeros, our wildcard mask is going to be 255.255.255.255. We want all of the interfaces that are up that have an IP address on router R3 to belong to area 0. And we should see that we form an adjacency with router R2. We do. Here's the router ID of our neighbor, R2, and we've reached a full state. We've fully formed an adjacency. Let's do the same thing on router R4. On router R4, let's go into router configuration mode for OSPF, process ID 1 I'll use again, and I'll say network 0.0.0.0, 255.255.255.255. Everybody belongs to area 0. And we should see a couple of adjacencies form now, one with router R2, we've reached a full state, and one with router R3, where we have reached a full state. And in the next video, we're going to give a series of verification commands to explore what's going on with this OSPF configuration, but I think we're good right now. I'm going to give just one verification command in this video, and we'll do lots more in the next video, but let's just do a show IP route command right now. And this is going to make sure that this router R4, has learned about all of the networks in our topology. The first thing I'm looking for is a collection of loopback IP addresses. For router R1, it's 1.1.1.1. For R2, it's 2.2.2.2. Here's the loopback IP address for R3, and of course myself, R4. I'm seeing all of the routers, and I'm just scanning through here, and yes, I am seeing every subnet in our topology represented here in the IP routing table. You might notice that the O flag indicates that we learned this via OSPF. However, notice that some of the O flags have an IA next to them. What's that about? Well, the IA means OSPF Inter Area. In other words, this network that we learned via OSPF lives in a different OSPF area. R4, it is entirely in the backbone area. It's in area 0. However, 1.1.1.1, it's in area 1, and therefore it's learned as an inter-area route. Same thing for the loopback IP address on router R2. That's an inter-area route. Same thing for the link interconnecting R1 and R2, and for the network connected to the fast Ethernet 0/0 interface on R1. And something else that we see evidence of here in this IP routing table is how OSPF is going to load balance across equal cost paths. For example, the network interconnecting routers R2 and R3, it's the 192.168.0.0/30 network. From router R4's perspective, it could get there via router R3, it could get there via router R2, and the cost is equal. We've got a cost value of 128. The 110, that's the administrative distance of OSPF, but we've got a cost of 128. And I've got the same cost if I go via router R2 as if I go via router R3. This means that I can do equal cost load balancing for this network. Coming up in our next video, we'll give several additional verification commands to check out the OSPF configuration that we just did.